we can do the knapsack problem. All right. And remember, we did knapsack in the greedy, but that was when you could take half of a bear. Right now it's integer, and we're going to come up with the dynamic programming algorithm for it. And you've heard me say knapsack is NP complete, in which case, why are we coming with the dynamic programming algorithm for it? It's a very good question. But it's a very classic problem that comes up in life all the time. And so we're doing it. And the problem is that the running time of this algorithm will still be exponential, right? But the nuance is it's polynomial in the number of objects. It's polynomial in the values of writing down the capacities. It's exponential in the number of bits to write the capacities down. All right, so there's the code. Okay, here, I don't know why I'm giving you this first. Let's see what we're doing. All right, I don't know why that's stuck in there. That shouldn't be stuck in there, but here we are over to knapsack problem. I was cutting and pasting old slides to make new slides, so who knows where things ended up. All right, what is our problem here? We have a knapsack, and what do we know? We know the volume of the knapsack, and we're running into a store, into a burning building, and we want to pack it full with as much as we can, maximizing the value of what we take. So every object, this is all the objects that are in the store. Each object has a value, no, a volume. V is for volume, a volume and a price, right? And what is the solution? A solution tells you what to put in the knapsack and what are our constraints. It's a valid solution if the sum of the objects that you put in the knapsack, the sum of their volume doesn't exceed the volume of the knapsack, right? So this is we're not doing packing. It's just by volume, right? And those are the volumes. I don't know what, and there's the total volume, so that's fine. Okay, what's the cost of the solution? It's the sum of the prices of the things you put in your knapsack, right? So you can imagine it just comes up in life all the time, right? Just your classic. I'm trying to maximize the values of what I take, subject to I have some constraints on what I can take, right? You can't get much simpler than this, right? All right. Oh, now we're doing the greedy criteria. Just the greedy to make sure that you've seen this already, but as a review, you can take the most valuable thing, right? But the problem is you should have taken the two objects, right? You could take the most densely. This is what we did for integer, for fractional one. We said we want to take the objects whose price per cubic volume is maximized, right? And here you take that, and that's great. But dude, you should have taken the wagon because it fills more of the knapsack, right? Everybody see that? If you allow fractions, then life is good, right? And it's a general rule. If you take the one way in industry of solving computational problems that are NP complete is the problem requires an integer solution, and you relax it to require a real solution. And then once it's a real solution, then we use linear programming. Remember linear programming to give you the optimal solution. And then you do some sort of probabilistically random, right? You say, hey, if I want a 0-1 solution and I got a 0.9, maybe I'll set it to 1 with probability 0.9, right? You know what I'm saying? And you hope for the best. That's what they tend to do in industry. All right, so now we're telling our story, and we're moving through life, right? There's our inputs, and they're in some order. We don't care about the order, but we're gonna go through them in that order, right? So here's my knapsack, and I'm moving through life, and I say, hey, my first object, what do I have to decide? Take it or leave it. Who tells us? The bird. You got it. You guys are really getting good at this, right? I say, hey, little bird, do I take that first object or not? She says yes. I put it in the knapsack. I go to the next object. I said, bird, do I take the next object or not? She says, no, I don't take it. I go to the next object. She says, yes, I take it. That's the game of life, right? Right, good. Now we're back to our frontline worker down in Chem H, trying to figure out what do we need to tell Trudeau? And do we tell him the number of objects considered so far? Yes, because clearly he needs to know what object we're working on, right? What else did you have to, you have to remember what has been kept so far? No. Do we have to remember the volume filled so far? Yeah, you got to know whether the next object fits, right? You need the volume filled so far, right? You got limited space as it gets filled, right? We got to be more careful about what we put in there, right? Yes, we definitely need the volume filled so far, right? So that gives us our table, right? Easy, right? So let's see what we got. We got our guy there, Pooh Bear sitting here. He's asking whether or not I should put the ith object in the knapsack. And J, actually, I changed this. Usually I was using a little v here, but I like everything I and J, so let's keep it as J, just so our sub-instances are J, right? So yeah, we have a knapsack whose volume is J. Well, we have a big knapsack that's filled up, and the remaining knapsack is a volume J, right? And we have put some things in here already. That's why there's only J remaining. And we need to know whether to put the ith in, right? There, what is the next object? We happen to know it's a block. And what is, so J is how much of the knapsack we have filled, right? So I assumed it was, no, I guess it goes this way, right? So maybe it's how much we filled so far. That's, I'm willing, yeah, it says right up there. Good thing that somebody can read what I wrote, all right? We could have done it the other way, right? But, all right, so we asked the bird. What do we ask the bird? Do we take the object? The bird says no. Where do we move? Down. We don't take the object. That moves us down. Our volume didn't change, right? But we've killed the ith object. We're onto the ith first object, right? And what weight do we put there? It says 0. Good thing I thought it was a test question, but actually the answer's there. So it makes it an easy question, doesn't it? All right, so why 0 is because we didn't get any new profit, right? All right, so then we're back here. We rolled our time back. The bird says, do I take the object? She says, yes, this time. So where do I go? Well, I put the object in. Yeah, I gotta go over and down, right? Right, so the volume, right? The volume, I go over from J to J plus VI. VI is the volume of the object. We know what the object is, right? So we know its volume, right? We move over that and we come down one. Right, everybody buy that? And what's the price of that edge? VI, thank you. Right, everybody follow this? It's the value of the ith object, right? It's the first time I taught it like this. It really is easier. I got to tell you, this is easier. All right. And then what? Now here's a little bug. What is this problem right there? That. Yeah. So that funny thing there is is that's required that I get it full, right? So we got to fix that, and we could fix that algorithmically, but I don't remember what I did, but you can fix it by adding things to the graph. What we're going to add to the graph is we're going to say, hey, dude, once we're at the end, I don't care what volume you have, right? So if the spends I land here, I've considered all the objects. Here, I guess I'm at n+1 because I've considered the nth object, right? So I've considered the nth object, and I have some volume. Hey, I'm willing to just go for free to the entity, right? We stick those edges in for free. That we didn't even have to change our code, right? Everybody follow that? Here's our reduction, right? We have our input, right? Our input tells us the volume and the values of each object, right? So we know how to add these edges. So from that we construct our graph, right? Which doesn't look very big, and then we send it overseas. It comes back, right? They're in a different time zone, so they can do it while we're sleeping, right? And that gives us our solution, right? Everybody got that? Couldn't be easier. All right. What's our running time? Well, the number of states in the graph, right? We have all the objects here. We have the volume of the knapsack here, and the degree is 2, and life is good, right? Until this guy comes up. When this guy comes up, then we got problems, right? He says, careful. Everybody remember what I'm careful about? I've said it already. It's NP complete, and it's because of that V. What's that V doing for us? V is a value, right? The input, right? So here, polynomial in what? What's the exponential in the size of the input? All right. So maybe I don't have slides here talking about it, but remember, if I write down right, I wrote that down really fast, right? Its size, how much work was it? 1, 2, 3, 4, 5, 6, 7. It was 7 work for me, right? The size of the input for me is 7. 8, did I count wrong? 8. But I did say Alzheimer's right. All right? All right, good. Right? But the value is bigger. Right? Everybody good with that? What are you doing counting my numbers? All right. So the value is big. Value is exponential in this. Right? And the proof that this is NP complete is really nuanced with the bits of this. We're going to be adding these bits, and we play with these bits where it actually adds up perfectly with the bits, and we make it NP complete, right? But is it really NP complete? Well, in industry, they don't care so much, right? Let's just round it up, right? This was good enough for us. And now it doesn't, I don't know, it's easier for us, right? Do they really care? Right, so now let's ask that question, do we really care? Right, so here, this is saying the running time is exponential in the number of bits to write V down, right? That's why it's incomplete. If you're really nuanced about the exact bits, you can cause yourself grief. On the other hand, if your knapsack is small or you don't care so much about the fine bits of the knapsack, then it's not really, right? So it's not really a problem. All right, so here, all right, that's what I said, NP complete, right? And what does NP complete mean? It means if you could get the exact answer per bit, then you can break all cryptography in the world, right? You can solve every NP complete problem, right? you're rich, but we no longer have privacy, right? It's an issue, right? I mean, you can no longer encode your password, which you now all know, right? All right, so, right, likely there's no polytime algorithm for all of these things. So likely you can't solve this problem fast. Now, can we get an approximate algorithm? All right. So, now we're going to say our running, you can choose your favorite epsilon. Epsilon's a little number. So let epsilon say be 0.001 or something, right? The running time is going to be n cubed divided by 0.001. So it's n squared times, help me, either 100 or 1,000. I lost track, right? And it will fit, you can do it so that it fits your knapsack, right? It's a valid solution, right? Because maybe industry cares about meeting needs, right? But do you have the optimal price? No, maybe not. But it's within a 1 plus epsilon of optimal, right? So, you know, that's pretty good, right? That's pretty good. Especially, so here I said 0.001, so you multiply by 1,000, right? That's pretty good. All right, there's our code. And we're on to another problem. How are people doing?